Okay, hello everyone in a new video in part 5 of chapter 10, which is the chapter of Archimedes upthrust in the third unit of mechanics. So now we are going to solve some exercises on what I have explained in part 4. So we have reached exercise number 9. A solid S of volume V is equal to 1000 centimeter cube. So the solid S given, so the volume is given by 1000 centimeter cube. Knowing that centimeter cube is not the SI unit of the volume, in order to convert from centimeter cube to the SI, which is given by meter cube, we multiply by 10 to the power minus 6. Then 1000 multiplied by 10 to the power minus 6. Then the volume of the solid S in the SI is given by 1 times 10 to the power minus 3 meter cube after plugging this on the calculator. And of density rho is equal to 800 kilogram per meter cube. So the density of the solid is given by 800 kilogram per meter cube in the SI. Floats on the surface of liquid whose density is rho prime. So the liquid has a density given by rho prime. And S is at rest, which means that we can apply the condition of equilibrium in this exercise. Take G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. Now 1.1. So here, just a side remark. Because the solid S is floating on the surface of the liquid, so the density of the solid is given by rho, and the density of the liquid is given by rho prime. So because the solid S is floating on the surface of the liquid, so the solid is less dense than the liquid, then we expect that the value of rho, which is given by 800 kilogram per meter cube, must be less than rho prime. So the value of rho prime must be greater than 800. Now 1.1, one of the two forces acting on S is its weight W, name the other force. So here let me do a small sketch. So let's suppose that this liquid is being contained in this container. Now here they didn't mention the shape of the solid, but let's consider that the shape of the solid is given by a cube. Now the shape is not important. So this is the solid S floating on the surface of the liquid. This is the liquid of density rho prime, and the density of the solid is given by rho. Now, because the solid S has a mass, then it will be directly subjected to the weight acting on the center of gravity vertically downward. So they are telling me name the other force here. Because we have a liquid, then the solid S will be directly subjected to the Archimedes upthrust force. So the name of the other force is given by Archimedes. Write down the vector relation between W and F. So the relation means the equality. In other words, they are asking me about the condition of equilibrium. Here we can use the condition of equilibrium because S is at rest. Then let's write as a title at equilibrium. Then how do we apply this condition? Always on the left we write the sum of forces acting on the solid S, and they are given by the weight and Archimedes upthrust force F. So W vector plus F vector is equal to the 0 vector corresponding for the equilibrium, and here we don't forget the vector over the 0. Now moving F to the right hand side, we have that the W vector is equal to minus F vector. Now the first equation tells us that the effect of both forces acting on the solid S cancel each other, whereas the second equation tells us that both forces have the same line of action, opposite direction, and same magnitude. So whenever we know the magnitude of one force, we can determine the magnitude of the other. Now in number 2, calculate the mass m of S. So this part consists of two questions, the mass and the value of the weight. So here, because we have the volume of the solid and the density, then we can calculate the mass using the relation given by that the density is equal to mass divided by volume, knowing that we are interested in determining the mass. So constructing the triangle of this formula, here because we have divide, then rho will be at the bottom. So putting our hand over m, then the mass of the solid, which is denoted by m, is given by the density multiplied by the volume. So here, because we are calculating the mass of the solid, so we must use the density of the solid and the volume of the solid. The density of the solid is given by this in the SI, and its volume is given by 1 times 10 to the power minus 3. Plugging this on the calculator, then the mass will be given by 0.8. Since everything in the SI, so the value of M will be in the SI, which is kilograms. So the mass is given by 0.8 kilograms. Now, moreover, in the same part, they are telling me to deduce the value W of its weight W vector. And by deduce, it means we need to use the part just previously before. In this part, we have determined the mass, and we know that the weight can be determined from the mass using the following formula, that the weight is equal to M multiplied by G. And here, let me stress, or let me mention the following. Here, this weight, what does it represent? The real weight or the apparent weight? So real or apparent. Why we need to distinguish between the real weight and the apparent weight? Because we have a liquid. But always, whenever we consider the weight as a vector, we are talking about the real weight and not the apparent weight, especially in the condition of equilibrium. So this weight, which is given by M multiplied by G, is actually the fourth property of this vector in the buildup. So here in this case, this weight represents the magnitude of this vector, okay? So now the mass that we have determined is given by 0.8, knowing that we are performing this experiment on Earth, so G is given by 10. Then the weight is given by 80 newtons because both mass and G are in the SI. So the value of the real weight is given by 80 newtons, the magnitude. So here let me write that the magnitude of the real weight is given by 80 newtons. And now in part 3, determine the value of the other force exerted by the liquid on us. So we need to determine the value of the force exerted by the liquid on us. So here they are referring to this force by its physical definition. So what's the force exerted by the liquid on us? We know that this force is the Archimedes upthrust. So they are asking me about the magnitude of this force vector, F vector. Knowing that the relation between W vector and F vector is given by W is equal to minus F vector. Then we are in part 3. From this vectorial relation, we are interested in the magnitude. So let's write down in magnitude. Now what will happen here that we will drop down the vectors and remove the minus sign. So W is given by F. But we have already calculated the value of W to be given by 80 newtons. So let's write but W is equal to 80 newtons. Which means then, since W and F are equal in magnitude, then F is equal to 80 newtons. So the value of the force exerted by the liquid on the solid S, which is the Archimedes upthrust, is given by F, is equal to 80 newtons. Now in number 4, they are telling me, knowing that the volume of the emergent part of S above the surface of the liquid is VE is equal to 200 centimeter cube. So the volume of the emergent part is given by 200 centimeter cube. So knowing that centimeter cube is not the SI unit of volume, in order to convert from centimeter cube to the SI, which is meter cube, we multiply by 10 to the power minus 6. Then 200 multiplied by 10 to the power minus 6. Then the emergent volume is given by 0.2 times 10 to the power minus 3 meter cube. So referring to this figure, what does the emergent volume represent? So this is the emergent volume. And it's given by 0.2. So the emergent volume is the volume that is not inside the liquid, it is above the liquid, okay? And the volume inside the liquid is the immersed volume. So this is the given. And they are telling me in number 4 to deduce the value of rho prime. What does rho prime represent? The density of the liquid. And by deduce, it means we need to use the part just previously before. In number 3, we have determined the value of the force exerted by the liquid on S, we know that rho prime and F are related via the following formula, that the magnitude of F upthrust is equal to the density of the liquid times the volume of the immersed part times G, knowing that we are interested in determining the value of rho L. So let's construct a triangle for this formula. Here, because we have a multiply, then F upthrust will be at the top, rho L, Vi, and G at the bottom, knowing that we are interested in determining rho L, which is denoted by rho prime, and it's given by the value of F upthrust, which is denoted by F, divided by the immersed volume, which is denoted by Vi, multiplied by G. Now the value of F is given to be 80 newtons, the value of G is given to be 10 newtons per kilogram. It's left to determine the volume Vi of the immersed part. So notice that the given is the emergent volume and not the immersed volume. So here what we have, we know that the total volume of the solid is given by 1 times 10 to the power minus 3 meter cubed. So we know the total volume, the outer volume of the solid S, to be given by V is equal to 1 times 10 to the power minus 3 meter cubed. And we know the emergent volume. So, but rho prime is given by the value of F divided by Vi multiplied by G. So in order to determine the value of rho prime, we need to know the value of Vi, which is the shaded part here, knowing the total volume and knowing the emergent volume. So all of these quantities are related via the following formula, that the total volume of the solid is given by the volume of the immersed part plus volume of the emergent part, and we are interested in determining Vi. So the value of V is given by 1 times 10 to the power minus 3 in the SI. So we keep Vi as a variable plus the volume of the emergent part, which is 0.2 times 10 to the power minus 3 meter cube. And here let me say the following, that when I have calculated the volume of the emergent part, I have expressed it in the following way, which is given by 0.2 times 10 to the power minus 3 meter cube. Although on the calculator, when we plug the value of VE, so which is 200 centimeter cube, the calculator will give the volume VE in the following form, which is given by 2 times 10 to the power minus 4 meter cube. But since the volume V is expressed in 10 to the power minus 3, so it's more convenient to express the volume V in the form of times 10 to the power minus 3. Okay? So for this reason, I have expressed the volume VE in 0.2 times 10 to the power minus 3 and not 2 times 10 to the power minus 4. So this is a side remark. Now, what's the type of this equation? This is a linear equation and one unknown. The unknown is Vi, so we put Vi on one side and all the other numbers on the other side. So Vi is given by 1 times 10 to the power minus 3 minus 0.2 times 10 to the power minus 3. Plugging this on the calculator, then the volume Vi is given by 0.8 times 10 to the power minus 3. Since both volumes here are expressed in meter cube, so the volume Vi will be expressed in meter cube. So this is the immersed volume. Now after we have determined the immersed volume, we can plug it here in this fraction. So the value of F is given by 8 and the volume Vi is given by 0.8 times 10 to the power minus 3. The value of G is given by 10. Plugging this on the calculator, it will give us 1000 kilogram. Sorry, 1000. Since everything is expressed in the SI, so the value of rho prime will be expressed in the SI, which is kilogram per meter cube. So the density of the liquid, which is denoted by rho prime, is given by 1000 kilogram per meter cube. So let's refer back to the early discussion that I have mentioned in this exercise. So the value of rho prime is given by 1000 kilogram per meter cube, which verifies the fact that the solid S will float inside this liquid, because the density of the solid, which is given by 800, is less than the density of the liquid, which is given by 1000. And let's move to the next exercise, which is exercise number 10. S is a solid body of weight W is equal to 3 newtons and volume is equal to 100 centimeter cubes. So W is equal to 3 newtons. Here, because we have, okay, so They didn't mention the liquid yet. So the volume of this solid is given by 100 centimeter cube. Knowing that centimeter cube is not SI unit of volume, in order to convert from centimeter to meter cube to centimeter cube to meter cube, we multiply by 10 to the power minus 6, knowing that meter cube is the SI unit of volume. Then 100 multiplied by 10 to the power minus 6 is given by 0.1 times 10 to the power minus 3 meter cube. Now the gravitational acceleration or the gravitational field strength is given by G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. And the density of water is given by 1000 kilogram per meter cube. Now the solid S is completely immersed in water, so this is important. And by this it means that the immersed volume is equal to the total volume of the solid S. So here, because they mentioned a liquid which is water, so let's discuss this weight. So they didn't mention whether this weight is real weight or apparent weight, so by default we take it to be real weight, because simply they didn't mention if it is the apparent weight, so we will consider it to be the real weight. Now in number 1, calculate the magnitude F of the Archimedes upthrust exerted by the water on S. So for example, we can directly think of the value of F, which is given by the real weight minus the apparent weight, but here we don't know the apparent weight, so we cannot use this formula. However, because we know the value of the density of the liquid, and we know the volume of the immersed part, which is equal to the volume of the solid because S is completely immersed, and we know the value of G, then we can determine the value of F upthrust, which is denoted by F, and it's given by the density of the liquid, which is denoted by rho, multiplied by the volume of the immersed part, which is Vi, multiplied by G. So, and here let's say, since S is completely immersed in the liquid, then the immersed volume, so the total volume of the solid S is equal to the immersed volume is equal to 0.1 times 10 to the power minus 3 meter cube, and they usually give a half a mark for this statement. Now let's rewrite the expression of F in terms of V. So replacing Vi by V, then the value of F is given by the density of the liquid times V times G. Now the value of rho is given by 1000, and the value of V is given by 0.1 times 10 to the power minus 3, and the value of G in the SI is given by 10. Now plugging this fraction on the calculator, then the value of F is given by 1, since everything is expressed in the SI, so the value of F will be expressed in the SI, which is in newtons. So the magnitude of the force vector F exerted by water on the solid S is given by F is equal to 1 in newtons. So F is equal to 1 in newtons. Now number 2, the solid S is left to itself. Okay, 2.1. Compare W to F. Deduce if S sinks or floats at the surface of the water. So first let's do the comparison between W and F. Then the value of W is given by 3 newtons, and the value of F is given by 1 newtons, and by compare we need to say whether one greater, so W if greater than F, less than or equal. So here in this case it's obvious that W is greater than F, and they are telling me to deduce if F sinks or floats at the surface of the water. And by deduce it means that we need to use the part just previously before. In this part we have done the comparison between W and F. So here let me do the following sketch. So this is the liquid contained in this container, and they are telling me that the solid S is completely immersed in water, so we don't know yet if it will float or sink. So this is the solid S. The forces exerted on the solid S are the weight acting on the center of gravity vertically downward, and F acting on the solid S on the center of gravity of the immersed part. So this is the immersed part. Then it has the same point of application of the weight W, so F acts vertically upward like this. So this is F. Now by comparing the magnitudes W and F, we need to deduce whether the solid S will float or sink. Now W is greater than F, and here referring to this figure, we can see that W is acting vertically downward and F acts vertically upward. Because the action of W is greater than the action of F, according to the comparison of their magnitudes, then we can say that the solid S will sink. So since the magnitude of W is greater than that of F, then S will sink. Okay, now in 2.2, calculate in this case the magnitude W apparent of the apparent weight of S. We know that the magnitude of F and the real weight and the apparent weight are related via the following formula, that F upthrust, which is denoted by F, is equal to the real weight, which is denoted by W, minus the apparent weight, which is denoted by W, APP, apparent. And we are interested in determining the value of W apparent. So the value of F is given by 1, the value of W is given by 3, minus W apparent. So what's the type of this equation? It's a linear equation and one unknown. W apparent is the unknown. So we put W apparent on one side and all the other numbers on the other side. Dragging W apparent to the left hand side, it will gain a minus sign, so it will become W apparent, which is equal to 3, keeping 3 as it is, and dragging 1 to the right hand side, so 1 will become minus 1. So this is equal to 2, since both 3 and 1 are expressed in newtons, so the value of W apparent will be in newtons. So W apparent is given by 2 newtons. And now in number 3, one can verify the results of 2.2 by comparing the densities. So here let me correct the following, that this is not 2.2 but rather 2.1. So one can verify the result of 2.1 by comparing the densities. So what's the result of 2.1? It is whether the solid S will sink or float. So 3.1, calculate the mass m of S and deduce its density rho S. So first let's calculate the mass. So we cannot use the density and the volume to calculate the mass because we don't know the density. So we'll use the mass to calculate the density. So we need to find another method to calculate the mass, knowing that we know the real weight and we know the value of G. So they are related via the following formula, knowing that we are interested in determining the value of m. So constructing the triangle for this formula, here because we have multiplied and W will be at the top, m and G at the bottom, we are interested in determining the value of m. Then m is given by W divided by G, referring to the triangle. The value of the real weight is given by 3, the value of G is given by 10. Plugging this fraction on the calculator, then the mass is given by 0.3. Everything is in the SI, so the value of m will be in the SI, which is kilograms. So the value of the mass is given by 0.3 kilograms. Now, in the same part, they are telling me to deduce its density rho S. So here, in addition to the volume, we have that the mass is equal to 0.3 kilograms. Now we need to determine the density, knowing that the density and the mass and the volume are related via the following formula, that the density is equal to mass divided by volume. No need to construct a triangle because this is the quantity that we want to determine, which is denoted by rho S. The value of m is given by 0.3 and the volume is given by 0.1 times 10 to the power minus 3 in the SI. So plugging this fraction on the calculator, then the density is given by 3000. Since everything in the SI, so the value of rho S will be in the SI, which is kilograms per meter cube. Then the density of the solid is given by 3000 kilogram per meter cube. So what does rho represent? It represents the density of water, which is the liquid. What does rho S represent? Represent the density of the solid. Now in 3.2, by comparing rho to rho S, so let's start by the comparison. The value of rho S is given by 3000 kilogram per meter cube, whereas the value of rho is given by 1000 kilogram per meter cube. And by compare, we need to mention whether the rho S is greater, less, or equal. So here it's obvious because they have the same unit. 3000 is greater than 1000, so rho S is greater than the density rho. They are telling me deduce if F sinks or floats at the surface of water. So because the density of the solid is greater than the density of the liquid, which means that the solid is more dense than the liquid, then let's say since the density of the solid is greater than the density of the liquid, then S will sink. So let's move to the next exercise, which is exercise number 11. The object of this exercise is to study the influence of the density of liquid on the flotation of a solid immersed in this liquid. In order to do this, we considered a solid cube S of mass m is equal to 0.9 kilograms. And of side A is equal to 10 centimeters. So knowing that centimeter is not the SI unit of length, in order to convert from centimeter to meter, we divide by 100. Then 10 divided by 100. Then the side of the cube in the SI is given by 0.1 meters. And G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. Part 1, characteristics of S. Okay, 1.1, verify that the volume of S is V is equal to 10 to the power minus 3 meter cube. So knowing that the solid S is classified as a regular shape because it's a cube, then its volume can be calculated directly from the side. So V is equal to A to the power 3. Now 0.1 to the power 3, plugging this on the calculator, then the volume is given by 1 times 10 to the power minus 3. Since the side is in the SI, so the volume V will be in the SI, which is meter cube. Then the volume is given by 1 times 10 to the power minus 3 meter cube. Now 1.2, deduce that the density of S is rho is equal to 900 kg per meter cube, and by deduce it means we need to use the previous part. In the previous part we have determined the volume and the mass already given to be 0.9 kilograms. We know that the density and the mass and the volume are related via the following formula. No need to construct a triangle because this is the quantity that we want to determine. The mass is given by 0.9 and the volume in the SI is given by 1 times 10 to the power minus 3. Plugging this fraction on the calculator, then the density is given by 900. Since everything is in the SI, so the value of rho will be in the SI, which is kilogram per meter cube. So the density of this solid is given by 900 kilogram per meter cube. Then now we are in part 1.3. Calculate the weight W of S. Because here they didn't mention whether it's the real weight or the apparent weight, so we take it by default as the real weight. So we need to determine the real weight, knowing that we have the value of m and we have the value of g. So W is equal to m multiplied by g. The value of m is given by 0.9 and the value of g is given by 10. So plugging this on the calculator, the value of W is given by 9, since everything in the SI, so the value of W will be in the SI, which is in newtons. So W is equal to 9 in newtons. So the value of the real weight is given by 9 in newtons. Now part 2 of this exercise, S is in oil. We immerse S completely in oil of density rho 1 is equal to 800 kg per meter cube. So by completely in oil, so it's being completely immersed in the liquid, so here we have that the immersed volume is equal to V. And the density of oil is given by 800 kg per meter cube. Calculate the value of F1 of the Archimedes upthrust exerted by oil on S. So let's discuss all the methods that one can calculate the value of F. So the first one is using the real weight minus the apparent weight. In this case, we cannot use this method here because simply we don't know the value of the apparent weight. Another method to calculate the value of F1 is using the condition of equilibrium. But here actually we cannot use the condition of equilibrium because yet we don't know if the solid S floats on the surface or is floating inside the liquid. So we cannot use the condition of equilibrium. They didn't tell me S is at rest or at equilibrium while floating on the surface. So the final choice is given by that the value of F upthrust, which is denoted by F1, is given by the density of the liquid. So here F1 corresponds to the force exerted by oil on the liquid on the solid S. So the liquid which is being used is the oil. The density of oil is denoted by rho 1 times the volume of the immersed part times G. Now let's say the following, that since S is completely immersed in the liquid, then Vi is equal to V. Now let's rewrite the expression of F1, replacing Vi by V. So the value of F1, what does F1 represent? It is the force exerted by oil on the solid S having the density rho 1 for oil, times the volume V, which is the total volume of the solid S, which is given by 10 to the power minus 3, times G. So rho 1 is given by 800 times the volume V 10 to the power minus 3 multiplied by 10. Plugging this on the calculator, then the value of F1 is given by 8. Since everything is expressed in the SI, so the value of F1 will be expressed in the SI, which is in newtons. So F1 is equal to 80 newtons. Now by comparing W and F, then first let's compare the values of W and F. The value of W is given by 9 newtons, and the value of F1 is given by 80 newtons, and by comparison we need to mention if W is greater, equal or less than, and here it's given by that W is greater than F1. Deduce that the solid sinks to the bottom of the liquid container, and by deduce it means we need to use the previous part. So in the previous part we have done a comparison between the magnitudes of the two forces being exerted on the solid S. Let me here make a small sketch. So this is the solid S being completely immersed in the liquid, yet we don't know if it will rise or sink. And it's being acted by two forces, by the weight on the center of gravity, vertically downward, and the force F having a point of application center of gravity of the immersed part. So the immersed part is the total volume. So the center of gravity is the same, of the immersed part is the same as the center of gravity of the solid S. So F will act vertically upward like this. Now knowing that the action of W, which is the magnitude, is greater than F, then in this case the solid S will sink. So since the magnitude of W is greater than that of F1, then the solid S will sink. And this is reasonable because now if we compare the two densities, the density of the solid is given by 900 and the density of the liquid, which is oil, is given by 800. Notice that 900 kilogram per meter cube is greater than 800 kilogram per meter cube, which means that the solid is more dense than the liquid, then the solid will sink. So here let me say that the result is sinks. Now in part 3, we repeat the experiment by immersing S completely in water of density ρ2 is equal to 1000 kg per meter cube. So here the density of water is given by 1000 kg per meter cube. 3.1, calculate the value of F2 of the Archimedes upthrust exerted by water on S. So here what we have done is we have repeated the experiment and we are immersing S completely in water. So here for sure we have that Vi is equal to V. So what are the methods in order to calculate the value of F? So the first one that comes to our mind is the real weight minus the apparent weight, but we don't know the value of the apparent weight, so we cannot use this method. The second method is the condition of equilibrium, which is W plus F2 is equal to 0 vector. Yet we don't know if this solid S will float or sink. They didn't mention anything about the equilibrium, so we cannot use this method. So we are left with the following choice, that the magnitude of F upthrust, which is denoted in this case by F2, is equal to the density of the liquid, and here the density of the liquid, which is water, is denoted by ρ2, multiplied by the volume of the immersed part multiplied by G. Now, what does Vi represent? It's the volume of the immersed part, because it's completely immersed in water, so Vi is equal to V. So let me mention that since S is completely immersed in the liquid, so they usually give a half a mark for this statement. Then Vi is equal to V. Now let's rewrite the expression of F2 replacing Vi by V. Then the expression of F2 is given by ρ2 multiplied by V multiplied by G. Now the value of ρ2 is in the SI is given by 1000, and the value of V, which is the volume of the object, is given by 10 to the power minus 3, and the value of G is given by 10. Plugging this on the calculator, then the value of F2 is given by 10. Since everything in the SI, so the value of F2 will be in the SI, which is in newtons. So F2 is equal to 10 in newtons. So here we have two forces. In addition to the weight, we have F1 is equal to 80 newtons and F2 is equal to 10 newtons. What's the difference between both? This is the force exerted by oil on the solid S, and this is the force exerted by water on the solid S after repeating the experiment and immersing S in water instead of oil. Now 3.2. So as you can notice that here in part 3 of this exercise, we are repeating the same steps of part 2. So in 3.2, deduce that the solid S floats on the surface of water. So they are giving me the results that the result that it will float. But here notice that comparing parts 3.2 and 2.1, there is something missing, which is the comparison. So first, let's do the comparison between W, not between W and F1, but rather between W and F2. Then we will deduce that the solid S will float. So we are in part 3.2. The comparison is given by that the value of W, the real weight, is given by 9 in newtons. Now, however, the value of F2 is given by 10 in newtons, and the comparison is given by that the weight is less than F2. So what does this mean? So we have that the weight is less than F2. So let's suppose that this is the force F2, knowing that the action of W is downward, vertically downward, whereas the action of F2 is vertically upward. And because the action of F2 is greater than the action of W, so S will rise to the top of the surface. So let's say since the magnitude of F2 is greater than that of W, then S floats on the surface of water. So the result of part 3 is given by that it floats. Condition for flotation. By comparing rho 1 and rho 2 to rho, so let me explain this. What do they mean by comparing rho 1 and rho 2 to rho? So first we need to do a comparison between rho 1 and rho. We need to compare them alone. And on the other side we need to compare the value of rho 2 and rho. Give the condition that must be satisfied by the density of a solid and the density of a liquid for a solid to float on the surface of the liquid. So they are interested in the case where the solid float on the surface of the liquid. So to which part this corresponds, to part 2 or part 3? We know that in part 2 it sinks, while in part 3 it floats. So this comparison, either between rho 1 and rho, or rho 2 and rho. So we are interested in this comparison because in part 3 the density of the liquid is given by rho 2. So we are only interested in this experiment because this is the case where the solid float on the surface of the liquid. So we are not interested in this. So the comparison is given by the density of the solid is given by 900 kilogram per meter cube. And the density of the liquid, which is given by rho 2, is given by 1000 kilogram per meter cube. And here the comparison is that the density of the solid is less than the density of the liquid. So rho is less than rho 2. So this is the condition that must be satisfied because we know that S will sink. Then the condition is given by when the density of the solid is less than the density of the liquid, then the solid floats on the surface of the liquid. And by this we have finished solving this exercise. So that's it for me in this video, guys. In the next part 6, we'll complete solving exercises on this chapter.